Okay, great. So yeah, my name is Stephen Hoover. I'm a data scientist at CIVIS Analytics. CIVIS is about 2 years old now. I've been working there for a year. Before that, my background is physics and astronomy altogether. I've been in the scientific Python stack for about 5 years, and it's wonderful. So today, I'm going to be talking to you about some of the predictive modeling that we're doing at CIVIS, how we're using Python, and I'll tell you about some of the choices we've made and lessons we've learned while writing this software. First, CIVIS. Sorry, the slides are getting a little cut off, but CIVIS is a end-to-end data science platform. It helps analysts work smarter, better, faster. It helps companies extract meaning from all of the data that they have. I'll give you a quick overview of the platform before diving into where the Python sits. The first step is bringing in your data, and CIVIS works with various sorts of data inputs, all the way from CSVs to databases of just about any sort. Once you have the data in the platform, then the next step is exploring and joining your data. You can use SQL queries to look into your data, to explore it. If you have tables with person-level data, CIVIS can match those together for you so that you've joined information about different people from different tables. Predictive modeling, in my opinion, this is the core of the CIVIS platform. I say that partly because that's the thing that I spend all of my time working on. But predictive modeling, you can do supervised learning tasks to figure out what exactly your data are telling you, and then take those models and apply them to new data to figure out something about the universe of data that you have in front of you. Making predictive models and having data is wonderful, but it's no good if nobody knows about it. So CIVIS has lots of built-in sharing capabilities, reports. You can use Tableau or D3 to visualize your data and share that with other people on your team. And all of this is with a focus on getting meaning out of your data, getting actionable information out of your data. One of the nice features about this is the automation. Once you've gone through this workflow, sure, maybe you could do it yourself on the command line or in your IPython notebook, but once you've done it once, CIVIS will automate this for you so that every morning when your database is refreshed, CIVIS will pull in new information, will update your models, will rescore and regenerate the reports. And we're leveraging cloud services for this, in particular the Amazon cloud services, and that means that you don't have to worry about any infrastructure and you can access this from any web browser anywhere in the world. All right, back to the predictive modeling capability. A lot of the pretty pictures that I just showed you, those are made with Ruby and JavaScript. There's bits of Go in there for speed. I mentioned SQL for database querying. But the predictive modeling, once you press run on that, all of that is being done in Python. There's, I think, maybe one call to an R function, but everything's really being done in Python. And we're running this Python code on EC2 instances in the Amazon cloud, and it's all wrapped in Docker containers. This is a really convenient way to deploy large-scale infrastructure. EC2, you can start up a new machine whenever you need one, and Docker gives you a nice convenient build environment so that you are certain what operating system you're using and what versions and which packages you have installed. All of that is taken care of. I don't think I have to work too hard to convince people that Python is a great choice for doing this kind of work. I used to work in C++. C++ is fun. Python is a different kind of fun. Python is a lot easier to develop in. It goes faster. I think it's a lot easier to read. It's easier to exchange code with your collaborators, read other people's code, figure out what a new piece of code is doing. One of the great advantages about Python, though, beyond just how easy it is for you to develop your own code in Python, is the large user base. Because there is such a large community around Python, it's easy to find answers to any of the questions that you might have. If you run into a problem with some odd behavior in dictionaries or lists, or you want to know how generators work, all of those resources are available online. And in particular, there's an extensive set of third-party libraries available in Python, really things that provide really core functionality. in CIVIS, we're leveraging very strongly libraries like NumPy, Pandas, and scikit-learn. We've put a lot of our own work into the CIVIS platform, but it would have taken at least 10 times as long if we weren't able to take advantage of the wonderful work that already exists in the Python community. NumPy, of course, is core to the scientific Python stack, gives you fast arrays and array manipulations. Pandas is great for dealing with tabular data, data I/O. Scikit-learn provides all the basic machine learning models, logistic regression, gradient boosting trees, all sorts of tools for working with those. All right, and that brings me to choices made, lessons learned. So the first of the choices made that I want to talk about is Python 2 versus Python 3. And at CIVIS, all of this Python code we're developing in Python 3. It's great to hear applause, thank you. It's a little weird that I even have to talk about this. I say on this slide Python 3 is the future, but really Python 3 is the present. Python 3 has been around for years now. Python 2 is no longer under development. There's a lot of fun new features in Python 3, so if you've been developing in Python 2, take a look at some of the stuff available in Python 3, like there's multiprocessing that I'll talk about in a moment, keywords like yield from, the async IO package, string handling, of course, is the reason that I have this discussion at all, I think. But if you are working in Python 2, a lot of people still are working in Python 2. There's sometimes good reasons to if you have a large existing code base. It's not difficult to make your code Python 3 compatible. Python 2 is, well, it's getting only security updates now. Those will cease in 2020. If you want your code to move forward, it needs to be in Python 3. And the first step, if you're writing in Python 2 now, is from future import division print statement. Start there. We can build on that. If you are moving from Python 2 to Python 3, the most obvious thing is that print is now a function. You use parentheses around it. Standard library is giving you generators instead of lists in a lot of places. The one subtle gotcha, at least from my point of view, is that division is now float division. And I think this is the right thing to do, but in Python 2, if you do 2/4, you get 0. In Python 3, it's 0.5. And that leads to some subtle bugs if you're converting code. Not that this has ever happened to me, no. Lessons learned. Python, it's a wonderful language. The thing that it doesn't do quite so well is using multiple cores on your computer. And that is entire talks in and of itself, but we have the multiprocessing module in the standard library. You can spawn off new processes to do extra work. I spent too long earlier this year just dealing with a interesting feature in some multiprocessing, in some linear algebra libraries. This applies in particular to the Accelerate library on OS X. It probably only matters if you're developing for OS X. It also applies to OpenBLOS compiled with the OpenMP, but by default it doesn't, so unless you try to hit this with OpenBLOS, you won't. But in particular, if you use linear algebra on two sides of a fork when you're developing on OS X, bad things happen. So if you build a machine learning model, if you build your machine learning model in your code and then you split off sub-processes to, I don't know, do cross-validation, then it just breaks. On OS X, I observed processes crashing. In OpenBLOS, it just hangs forever. Neither of those are great. Python 3.4 introduces a new multiprocessing context they call fork server. It has better isolation between processes. You lose some of the implicit memory sharing from the default fork state, but it avoids this multiprocessing linear algebra bug. Something to be aware of if you're working with multiple processes. Next of the choices made, and this is more of a global thing, but at CIVIS, the data scientists are writing production code. And I think overall this has been great for us. The people who know the machine learning models, the people who understand the data, are the people who are writing the code that our clients are running. So that predictive modeling, that has a lot of code that I have typed myself into the computer. And the alternative, of course, is to have your data scientists develop these models, block them out, and then hand them off to software engineers to implement. I think compared to that model, having the data scientists write production code lets us ship faster, and it avoids problems in maybe translating your code to a different language or a different paradigm. The cons, of course, are that software engineering is really an entire skill set, and just because you can write Python code that develops good models doesn't necessarily mean that you know what it takes to ship production code. So that's an extra skill set that you have to learn. Talk to the software engineers that are working with you, find resources online. Lessons learned. Testing. Testing is really, really good. In particular, if it's not tested, it doesn't work. And you may think it works. There's been more than once that I've written code, it works, I've typed stuff in, it gave me answers that I wanted. But then as soon as I sat down to test it, the very first unit test broke. So definitely test. Unit test is a module in the standard library. It's very important, make sure to use it. NumPy has a testing module that you can use to do numerical tests, compare arrays, for example. Special shout out here to the Nose module. Nose is not standard library, but if you're developing code, if you have a lot of tests in your code base, Nose will run through all of them, run them all at once, give you a report back on that. In particular, there's a -- with coverage option when you're running from the command line, and I found that's very useful for figuring out, it will give you a report about which lines of code you've actually contacted in your tests. And just because you've used a line of code in your tests doesn't mean that it's working, but if you haven't used a line of code in your tests, it's probably broken. So you should expand your tests until you're covering everything that matters. Also, I recently discovered the unittest.mock library. This has been promoted to standard library in Python 3. It's magical. Okay, choices made. The last of the choices made that I want to talk about. When you're designing a new project, you have to think about the scope of the project, and you have to think about what cases it's going to cover. At CIVIS, we want our library to be reusable. We, in particular, want it to be extensible because we want to build on this and add capabilities continuously in the future. And we want it to be, well, generic is maybe a bit too strong of a term. There's no way that you can actually model everything possible in the world. So you have to start by making some assumptions about the kinds of data that you're going to look at. And the CIVIS modeling library right now is working on dense tabular data with a single outcome column. Now that outcome column, it might be binary, it might be categorical, it might be ordinal, it might be continuous, but it exists, there's only one of them, and each row has sets of features. There's an example there of a data set that shows the sort of data that I'm talking about. And why did we choose this kind of data? It really covers a wide variety of business use cases. I think more than the fact that it just covers a wide variety of use cases, there's a lot of ways you can go with machine learning and a lot of things you can learn from your data. For example, clustering algorithms might tell you something about the structure in your data, but supervised learning on single labels, it's not only more easily actionable, it's also easier to understand and work with. So we aren't necessarily able to educate all of our users in some of the subtleties of data analysis or data science, but it's easier to understand. You have this example, you have this outcome, and then you can train the model such that with a new example of a similar sort, you can predict that outcome, and then you can take that and you can use that in the wild to bring advantages to your organization. Lessons learned, writing extensible code. There are things you have to think about if you're writing code and you want to go back to it later and add more capabilities. In particular, you need to think about having a well-defined API. Things get chaotic if different functions and different classes in different parts of your code are interacting in different ways. Documentation is vital. You're probably not going to remember what you did a month from now, much less what other people did a year ago. And writing extensible code is, in my experience, quite a challenge. So you need to sit down, you need to think about where you want your code to go, what use cases you want to be covering in the future. You want to write your code to cover those, to be able to be expanded to cover those use cases. But I think the biggest lesson I've learned about extensible code, writing extensible code, is that you will fail the first time that you try this. It could be that you're all very much smarter than I am. That's probably true. So I will fail at writing extensible code. If you want to write extensible code, you just have to be willing to go back and refactor. Several months down the line, you'll realize that the new use case that is quite an obvious thing to do is actually difficult to shoehorn into your old code, and there's an obvious way to rearrange your class structure, for example. And if you want to keep expanding this library, at some point you have to be willing to sit down and refactor it. So in conclusion, Python language is really great for developing big projects. I think it's helped us a lot at CIVIS. A vital part of that is the huge open source community and all the tools available. So make sure that you are not repeating something that somebody else has already spent years of great work doing. Go out and use that and jump off of that to build your own product. And think about what you're doing, plan ahead, but be willing to go back and refactor. All right. Thank you. All right. Questions?
So I was wondering, you said that there's a lot of great things sort of about Python for data analytics. Are there any things that you feel are missing, like things that you would like to see created in the next couple of years?
I don't have, so oh, I guess that was picked up on the microphone. I don't have any specific examples of that right now. So I think the statistical modeling and machine learning capabilities in Python have been expanding quite a lot. 2, 3, 4 years ago, I would have said that R had a lot more libraries built up for the kinds of statistical modeling that we're doing. And as I said, we're still calling an R package. GLMNet is a very nice one. We have a couple of others that we like. But those capabilities are rapidly appearing in Python, and I don't think there's any significant thing, there's no major thing left to be added, I'd say, but more statistical modeling capabilities are always welcome.
Awesome.
Other questions?
How hard was it to get the data from Amazon EWS or EC2 into Python?
It's not difficult to get the data into Python, assuming the data aren't too large. So we store data in Amazon Redshift, which is a relational database, and that's really fast at running SQL queries. It's also really fast at dumping the contents into flat files, and then the flat files can be read into your favorite modeling algorithm with no problem. It gets a little less convenient if you have, say, 500 gigabytes of data, but the modeling cases that we're dealing with are primarily small data, small to mid-size, I'd say. We have other solutions for larger data.
Any further questions? Okay, thank you very much, Stephen.
Thank you.